The emergence of the transistor shook the world. It certainly shook the vacuum tube makers. Some believed that the category was a dead man walking. The transistor was going to replace the vacuum tube everywhere. But the iconic American company RCA believed that vacuum tubes still had a future, and in 1959 they poured all their skill and knowledge into one quote-unquote revolutionary tube. In today's video, RCA and the vacuum tube's last stand. In the late 1800s, a number of scientists noticed that a stream of free electrons can carry an electric current across a vacuum. Though I have to note that at the time they didn't know about electrons. They would not be discovered and named until 1897 by J.J. Thomson of Cambridge. The famed inventor Thomas Edison then helped take the next step whilst working out an issue with his incandescent light bulbs. Such bulbs worked by heating up a carbon or tungsten filament until it glowed. He, or his team, noticed that if you put a metal plate inside the bulb at the other end of its filament and connected a battery, then a current can flow through in one direction. He patented this and they named it after him, the Edison effect, but he did nothing with it. A few years later, in 1904, the English physicist John A. Fleming understood the Edison effect's potential and used it to produce the first thermionic tube. The Fleming tube, as it is called, had the key elements of the vacuum tube. First, an electron source dubbed the cathode. The Fleming tube used that carbon or tungsten filament. You heat it up, and it throws off electrons. Second, an electron collector dubbed the anode. This is a plate that connected electrons when positively charged. The Fleming tube was a diode, a one-way path for current. Fleming used it for an electronic tool to rectify oscillating radio signals so they can be detected by a galvanometer. The resulting device was excellent for detecting radio signals. The American engineer Lee DeForest read about Fleming's work and added a wire mesh called a control grid between the cathode and the anode. This grid can be charged in such a way to either accelerate or dampen the flow of electrons from the cathode to the anode. Now, you not only have a workable electric current switch, but also an amplifier. AT&T recognized as such amplifiers can improve the quality of their long-distance phone calls and purchased the patent from Lee DeForest. But DeForest's tube design still suffered reliability issues, so AT&T passed it off to their vaunted manufacturing arm, Western Electric. Those guys improved the design, completely evacuating the chamber, changing the filament composition, and strengthening the internals. Vacuum tubes thus went on to dominate the electronics world for the next 50 years. But that didn't mean people were entirely happy with them. System designers using them found them large, bulky, delicate, hot, and power-hungry. They were basically incandescent light bulbs. They run hot, and the thermal stress of which frequently caused them to shatter. The famous ENIAC computer had 17,000 vacuum tubes, and they broke down a lot. Every time it happened, operators had to go find which one. One of the largest sellers of vacuum tubes in the United States was the Radio Corporation of America, or RCA. And for them, vacuum tubes are not just another product to sell. It was core to their strategy. Famously, RCA was created in 1919 as an American-owned consolidated entity that received critical U.S. radio communication patents from the foreign-owned British Marconi. The Navy had pressed for the sale and transfer of those patents for national security reasons. Other patents from GE, Westinghouse, United Fruit, AT&T, and others were later added as well. Representatives from these companies joined RCA's board. In its early years in the 1920s, the company operated as a simple patent pool trust, taking fees on its key radio-related patents. Other companies like GE and Westinghouse made the actual hardware, which RCA distributed and sold. However, RCA's practices bedeviled independent radio makers. It charged high fees to license the key wireless patents, something like 7.5% of gross sales. They also forced those radio makers to only buy and use RCA components, including its vacuum tubes. The U.S. government sued over this, and in 1931, a judge determined that these exclusive vacuum tube contracts violated an antitrust prohibition on tying, a practice where buyers must take B to get A. This and other court decisions forced a change. In 1932, GE, Westinghouse, and others had to sell their shares and pull their board directors, giving RCA independence. But the company was then already in the midst of a generational change. In the 1920s, radio was a strict point-to-point technology, a vital but dull communications utility for boats. RCA CEO David Sarnoff reimagined radio as an entirely new form of mass media, a, quote, radio music box, end quote, bringing music, news, and sports to people's homes. He and RCA turned this vision into reality, building a vertically integrated radio ecosystem that included media, broadcasting stations, and manufacturing. Meanwhile, RCA opened up their patents a bit more broadly and started using the licensing fees they earned to fund R&D into emerging technologies like the television. The company's trove of patents grew rapidly in the 1930s. In 1929, RCA had just 1,183 patents. By 1944, that had surged to 8,258, most of which were developed internally. Licensors were no longer forced to buy RCA vacuum tubes, but those tubes nevertheless remained a profit center. Selling high-margin replacement tubes for radios and TVs made RCA a pretty penny. In the early 1950s, RCA held about 25% market share of the world tube market. Now, people have been searching for a solid-state version of the vacuum tube for years. So after AT&T Bell Labs announced the discovery of the first transistor in mid-1948, a swarm of article writers claimed that the transistor will be able to do everything the tube can without its shortcomings. Bell is usually a restrained company, but even they seemed overwhelmed by the possibilities presented by this pea-sized thingy. They built oversized models of their transistor for marketing and sent their scientists around the nation to give talks. A solid-state vacuum tube drop-in replacement puts RCA's entire lucrative tube business at risk. When the news of the transistor hit the newswire in July 1948, RCA immediately set their R&D teams upon licensing AT&T's patents, replicating the results, understanding the technology, and start producing their own patents. RCA soon recognized that though the transistor was indeed revolutionary, it was far from a suitable drop-in replacement for the good old tube, especially at the start. To start, they were delicate. The first transistor, called the point contact transistor, consisted of two very fine wires barely touching a solid piece of germanium semiconductor material. Just looking at it, you feel it too fragile for real-world use. The wizards at Western Electric produced the more manufacturable point contact design, shrinking it down and putting a case around it, but it can still randomly fail if, for example, its tiny wires happen to break away from the germanium, which it often did inexplicably. New types of transistors soon thereafter emerged to replace the historic but largely impractical point contact transistor. The most manufacturable were the junction transistors, which rely upon junctions of alternatively doped germanium or silicon to move charge carriers. But even those sturdier transistors were still quite tricky to manufacture. In 1953, 5 years after the Bell Labs announcement, big companies like Western Electric and Raytheon produced only about 50,000 transistors in 12 variants each month. Businessweek would report that in 1956, semiconductor companies sold a total of 12.5 million transistors, though growing fast. To compare, that same year saw 474 million vacuum tubes sold. And finally, there are many jobs done by tubes that transistors cannot replace and might not be able to replace for many years more. For example, jobs that demand high performance in the high-power, microwave, and general radio frequency fields. So RCA recognized that the transistor threat was not quite the asteroid hurtling towards their business, more like the flood rising around their knees. In response, they decided to take dual paths. In the first path, RCA kept researching solid-state technologies with an eye towards eventually incorporating them into end-user products. In the second path, they sought to evolve the tube and have them do what the semiconductors of the time cannot: advancing knowledge of semiconductor physics, newly commercialized materials, and improved manufacturing technology would together revolutionize vacuum tube design and production in the 1950s. For example, new high-temperature ceramics, improved mechanical designs, and vapor/water cooling made for sturdier products that better resisted heat, jostling, and vibrations. And to produce tubes capable of handling some of the highest frequencies without overheating, tube designers incorporated parallelism. So instead of having just one big cathode grid anode set, you stuff many dozens of smaller sets into one tube. Such new innovations meant that, counterintuitively, the 10-plus years after the transistor's invention saw something of a vacuum tube boom. Observers noted a plethora of new tube sizes, shapes, and capabilities. Between 1958 and 1962, RCA by itself developed and introduced 800 new models of tubes. In 1959, RCA mustered the latest in vacuum tube technology to produce a tube it called revolutionary. They positioned it as the tube capable of going toe-to-toe with the transistor in terms of size, performance, power usage, and reliability, the Nuvistor. According to RCA, the name Nuvistor was coined out of two words: nueva, meaning new, and vista as in prospect. RCA wanted to convey the idea that the Nuvistor was a new look at an older thing, the tube of tomorrow to challenge the growing transistor. Regardless of the marketing, the Nuvistor works using the same principles of thermionic emission used by every other vacuum tube in existence. The big differences were its size, durability, and performance. The Nuvistor is very small, just about half an inch tall. It is about as big as a thimble, if you know what that is. It is small enough to mount right onto a circuit board, like a transistor. The second thing you will notice is that there is no glass. RCA removed all the glass and mica to eliminate sources of thermal stress and enable survival at higher temperatures. Glass tends to shatter at higher temperatures. They gave it a metal body, a solid ceramic base, and affixed each electrode at just one end via a cantilever design. All of this allowed for more resilience against outside shocks and vibrations, as well as thermal stress. This new cantilever design also allowed RCA to more easily assemble the tube. You start by loading its various components together into a jig upside down. The mount is then put into a high-temperature brazing furnace. Inside, a metal filler melts down and joins the parts together. We then add on a cathode cup to finish the cathode, stick the thing into a protective outer envelope, create the vacuum inside it, and then finish the Nuvistor assembly in a vacuum. RCA announced the first Nuvistor model, numbered the 7586, in March 1959. They sold quickly enough for RCA to introduce 7 more models alongside it. Some of these, like the RCA 7262 and 7263, were developed with military sponsorship. In 1962, RCA announced that they have made and sold over 2 million Nuvistors. RCA Division VP John Farese told reporters that demand was, quote, so great that we produced over 1 million units in the past 5.5 months, end quote. Defense buyers especially liked its size, ruggedness, and high performance: sonar, airborne weather radars, satellites, and test equipment. It is genuinely good for low noise, very high frequency, and ultra-high frequency applications. The tube also made an appearance in RCA's color televisions in the 1960s, where it helped boost TV picture power by significant amounts. Various RCA Victor sets advertised it as helping to eliminate noise and snow. The tube also performed admirably in high-end audio equipment, FM tuners, tape recorders, and microphones. I think some of the most well-known end-use cases today are in high-end audio. However, customers did not quite receive the Nuvistor as the revolution RCA wanted. 2 million tubes sold sounds like a lot, but remember, hundreds of millions of tubes were being sold each year. Transistor volumes were far lower, but were surging 3 to 4 times year over year. I think the price might have had something to do with it. RCA quoted a distributor resale price of $480 or $5,500 today for the first RCA Nuvistor 7262 and $690 or $7,900. Rising transistor volumes, on the other hand, caused their prices to fall. In 1958, Fairchild was selling transistors made from silicon, which performed better than older germanium, at about $150 each. That was the most expensive those transistors would ever be. Ultimately, RCA decided to continue the niching down of its vacuum tubes. Their next big thing after the Nuvistor were its Thermalox power tubes, which amplified RF signals to high power levels so that they could be sent across longer distances. RCA proudly noted in its historic retrospective that a Thermalox tube was employed inside NASA's Pioneer 5 Venus probe. A new business department was set up to develop and sell specialty tubes for use cases like this. This nichification of the vacuum tube successfully defended RCA's vacuum tube business for a time, but it was a Pyrrhic victory. Remember how I said that RCA built up this massive patent pool during the 1930s? The company's dirty little secret was that even as it became a media empire, patents still underwrote much of its work, just in a different way. The company did not allow licensees to just license a few key patents, like those foundational TV patents. Rather, they had to license the whole pool, including those they did not want. It was like the old cable TV model. If you want to watch ESPN, then you have to pay for all these other channels. The US government saw that as more tying. After World War II put a pause on antitrust activity, the government revitalized its chase, urged on by independent TV equipment makers like Zenith. And finally, in 1958, RCA and the government settled a consent decree that forbade the practice for domestic companies. Now, American companies like Zenith can license RCA's patents royalty-free. This had massive, unforeseen consequences down the line. As Willy Shih noted in his famous Harvard Business case study, the consent decree put no limits on RCA getting royalties from foreign licensees, so they turned to serving Japanese companies, at least 82 of them, and much later a particular Taiwanese research institute. This armed Asian technology companies with TV and semiconductor IP that eventually allowed them to come and compete with American firms. Despite pioneering many semiconductor technologies that went on to be significant, RCA never gained the same prominence in solid state that it once had in vacuum tubes. The company repeatedly missed creating or catching up to key technical milestones, like the first commercial silicon transistor, which was a grown junction silicon transistor made by Texas Instruments. Silicon helped close whatever performance gap there was between the Nuvistor and germanium, and unlike vacuum tubes, transistors do not need energy to heat up a cathode. As silicon moved down the price curve with integrated circuits, the Nuvistor fell behind and was discontinued in the early 1970s. RCA also seemed to struggle with incorporating solid state into their devices. In the end, it was TI again, Sony and the other Japanese companies, that produced the first transistorized radios, TVs, and calculators. Radios! That was RCA's jam. That should have been a no-brainer. This failure to bridge research and product can be blamed on a mission gap between the two divisions inside the company. The loss of patent package revenue forced RCA Labs to take many more defense contracts. By the late 1950s, defense contributed as much as 75% of lab revenue. While defense was famously an early demand driver for transistors, in the case of RCA, defense projects diluted resources and hived off the research teams by sending them down niche technology paths like gallium arsenide. Meanwhile, the RCA factory team struggled to get their silicon lines running, complaining that their R&D teams were, quote, too many years ahead of itself, end quote. Perhaps cognizant of its declining fortunes and its core business model, RCA became a conglomerate. Starting in 1965 with the acquisition of the publisher Random House, RCA went on to buy a bunch of unconnected businesses like frozen food, car rental, real estate, and carpet. Their decline goes on from there. For those interested in RCA's fascinating business model and its changes over the years, I want to point you to the work of Shigehiro Nishimura and Hyung-Sub Choi. Both have published papers on this, and they are both amazing. Before we close, I want to give my thanks to viewer Henry, who first brought up the Nuvistor to me. It led me down a rabbit hole, but here we are. Ironically enough, I think someone can make a credible argument that RCA's successes with the tube line diversification distracted the company at a time when it should have been looking ahead. When the transistor emerged in 1948, people saw it as merely a replacement for the tube, somewhat understandable since engineers were most familiar with the tube, and the transistor can amplify signals too. But the years since have shown us that while there were some overlaps, these were two different devices. Vacuum tubes have continued their nichification, delivering performance in areas transistors would not be able to match for decades. Even today, some high-power radar, microwave, and broadcast systems still use what are now called vacuum electron tubes. The transistor, however, ended up creating a vastly larger market because of how it enabled entirely new things, like portable devices and digital computers. In the end, transistors were far more than simple drop-in replacements for the vacuum tube. RCA, the vacuum tube king, saw the threat, but not the opportunity. Alright everyone, that's it for tonight. Thanks for watching. Subscribe to the channel, sign up for the Patreon, and I'll see you guys next time.